Alright, hello everyone. It is late today. 10:08 p.m. Today is the last day before my internship ends, so it's exciting. We're gonna continue on with some graph stuff. Let's see. Wanted to have this run of the You might hear my cat in the background. I got a new cat. And my old cat is just not driving very well, so he's yelling at me about that. But not much I can do. Just gonna have to deal with it. So the last time we were doing this problem, which I knew it was Dijkstra's, I just couldn't figure out how to do Dijkstra's. I haven't done Dijkstra's in a minute, and so I just kind of copied and pasted off of what Neat Code wrote. Mr. Neat himself. So actually, before I start on the next problem, I'm going to read over this so we can truly understand it. So here we're building our adjacency matrix, which makes sense. Okay, so what he's doing here versus what I was doing last time. So he's initializing a min heap being completely empty. Beforehand, I was trying to initialize it with infinite edges. Sorry, nodes of infinite length, and then just minimizing it. And then he also has a visited set, which makes sense. It's hashable. Okay. So if we pop it, we get the most minimum. We say we visited it, and then we check every single neighbor. And if the neighbor hasn't been visited, then we push the heap plus the new distance. Okay. That makes sense. Now let's do reconstruct itinerary. Oh my god. You just have to bear with me on this one. He likes to meow 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 until the sun shines. He will meow your ear off and he does not care. So sorry about that. Perks of having a cat. They're really cute, they're really awesome, but they're also really annoying. You are given a list of airline tickets, where each ticket has a from and a to, represents the departure and the arrival airports of one flight. Reconstruct the itinerary in order and return it. All the tickets belong to a man who departs from JFK. Thus, the itinerary. Hey! Stop it. Thus, the itinerary must begin with JFK. If there are multiple valid itineraries, you should follow the itinerary that has the smallest lexical order when read as a single string. JFK to Atlanta. Hey, fucking relax, man. Goddamn. You're tweaking. Stop it. Stop tweaking. Wait, so this is deceiving. Like, very deceiving. Because at first it just seemed. I mean, this seems like regular BFS to me, or DFS to me. I'm guessing it's not. Hey, shut up, dude, please. Yeah, see, that's edge log edge. Use okay, so here, that's the trick. You have to utilize every single one exactly once. I think I remember doing some sort of complex algorithm that was for that. I can't remember what it was for though, so we're just going to keep opening up some things. How do you ensure the smallest flexible order is maintained? We build an adjacency list, of course. Yep, typical. From DFS, yep. To construct the result, but we first sort the neighbor's list of each node to ensure small flexible order. Yeah, no, okay. I mean, yeah, this all makes sense. Okay, but the problem I'm seeing is, like, what if the small... what if the smallest one... Hey. Ease it. Relax. God damn it. Yeah, it would be naive. But what I'm wondering is, like, something like this, right? Oh wait, no, this isn't possible. Anyways. Oh wait, no, something like this. Here you go. This is fine. So if this is like an A, this is like a B, and we are starting off here. If I go to this A, I just... Nah, I can't go anywhere. You know? So this can't be just greedy. Unless if the problem ensures that every single case does not have that problem. I don't think that would make sense for them to do that, though. So I'm doubting that's gonna be the case. Let's read some more hate. In this approach, we traverse reduce by moving the neighbors reversing, and then perhaps an advanced algorithm that incorporates DFS might be helpful. Never touch this algorithm. We can use High-Holzer's algorithm, a modified DFS approach. Instead of appending the node to the result list immediately, we first visit all its neighbors. As well as a post-order traversal. After completing all DFS calls, we reverse the path to obtain the final product, which is also called Euler path. Ah, wait, I think I did do... This is beyond me. Oh, shit. Yeah, we're gonna go through. I'm gonna sort each one. Graph theory is pretty cool. I wish I took a. I wish I took a graph theory class. Just because I forgot the this thing. Yeah. Okay. There you go. I fixed it. Choose any starting vertex V and follow a trail of edges from that vertex until returning to V. It is not possible to get stuck at any vertex other than V because in degree and out degree of every vertex must be the same. Oh, dude, I remember that as well. When the trail enters another vertex, W, there must be an unused edge, leaving W. The tour formed in this way is a closed tour, but may not cover all the vertices and edges of the initial graph. What? This looks horrible. You know what am I expecting? I'm on Geeks for Geeks. Shit's ass, respectfully. Circuit algorithm.
So the goal of this video is to give an example of Herholzer's algorithm to find an Eulerian circuit. So here we have a graph that's connected, and we know it's Eulerian because its degree sequence is all even. So how do we find an Eulerian circuit? So the first step is to find a circuit in the graph. So for example, I'm going to start with this 4 cycle in the bottom. And I'm going to call this R1. So R1 contains vertices 3, 4, 5, 6, 3. So if this circuit does not cover all the edges, I find an edge incident to a vertex in R1 that is not marked. So for example, this edge here, 2, 3. Next, I find a circuit that contains that edge E. So for example, that edge E belongs to this triangle here. 2, 3, 3, 1, and 1, 2. So now I'm going to patch my circuit R1, including this new 3 circuit. So what does it mean patching? So since I visit that, since that triangle is incident to vertex 3, I'm going to patch R1 and I'm going to include that 3 cycle here. So that 3 cycle covers vertices, say 3, then 2, then 1, and I'm back to 3. Okay? And now if the circuit has covered all the edges, I'm done. If not, I find a vertex that's incident to an edge that I haven't covered. So for example, I haven't covered this edge 1, 5. So this is going to be my new edge, E. And again, I find a circuit containing this edge. So for example, this circuit, this edge belongs to this circuit of length 4 here. Okay, so now again, I'm going to patch my circuit by adding this circuit of length 4. Okay, so what has been patching? So, for example, right after vertex 1, I'm going to include this circuit of length 4. So that would be, say 1, and then I go to 5, and then I go to 2, and then I go to 6, and I go back to 1. Okay?
Oh shoot. Okay. That did a full circuit. Well, that's interesting.
And now this circuit does contain all the edges, so this is an Eulerian circuit. So let's check that this indeed is an Eulerian circuit. So I start at vertex 3, I go to vertex 2, I go to vertex 1.
So
then
it looks for loops. Another thing I could do is like interesting. There's multiple Illyrians you can create. pop it. So this is a stack orientation. Okay. See if I can implement that with off the top of my head. So while I actually have data in there, wait, do I pop? No, I don't pop. Is it capital P? No. So I'm assuming that based off how he said it, this might be reversed. So I only popped JFK. Mainly because I also spelled it wrong. See if that actually has to change, though. Did you look at that? Oof. Nope. Nope, that's not right. Oh, probably it returns null. Some shit like that. Oh, I mean, yeah, okay. Fair. Hmm. Interesting. Should I sort it the other way? How do I do? What's the word? What's the word for like incrementing versus decrement? Descending. I'm just throwing shit at the wall right now. I don't think. Oh yes. Okay, cool. Oh, beautiful. I didn't understand much of that, but hey. That's a pretty nifty algorithm. Not gonna lie, it's really short and sweet. I like it. Alright, well that's gonna be it for today. Just gonna be that single problem. I had to use some help to get along the way, but at least it wasn't as bad as yesterday. That's an algorithm I've never touched before. It's pretty interesting. But yeah, thank you for watching, and I'll see y'all tomorrow.